Kia ora and welcome back. In this video we're going to continue our discussion about subgroups, and we're going to look at a particular one that's quite important, and it's called the centre of a group. So every group has one of these, and essentially it's like the abelian part of a group. So a lot of the groups we'll be studying are not abelian. Okay, the order in which you do the group operation matters, but there's usually some elements, and it may just be just the identity, that actually end up commuting with everything else. So that set of elements is actually a subgroup in and of itself, and it's called the centre. Okay, so here's a slightly more technical definition of that. So the centre of a group is the set of all elements in G that commute with every element of G. Okay, and we can write that in set notation, where Z of G is the set of all things in G such that for every single element of G, that element A commutes with the element X of G. So it's like the commutative part of a group. So let's just make a little note about that. So the centre is like the commutative part of a group, or the abelian part of a group. Of a non-abelian group. Okay, and clearly if the group is actually abelian itself, then the centre is going to be all things in the group. So if the group is abelian, then we have that the centre, Z of G, is just equal to G itself. Okay, so we've claimed it's a subgroup, but we haven't actually proven that yet. So before we actually show some examples of this, we'd better prove that the centre of the group is in fact a subgroup. Okay, so here's our theorem. The theorem is just literally that the centre of a group is in fact a subgroup. So we're going to use the two-step subgroup test. So remember, to start with that test, we need to show that the set is non-empty. So we've got a definition of our set up here. Here it is. And we're going to work with this and show that the set is non-empty, that it's closed under inverses, and that it's closed under the group operation. Okay, so we're working completely in general for any old group. So the first thing we have to do is note that the identity, or we'll show that the set is non-empty, and like I said before, the way we usually do that is to show that the identity is in it. So, is the identity in the group? What does that mean? Well, that just means that the identity needs to commute with all elements of X. So that's part of the definition, in fact, of the identity. So no matter what X is, EX is equal to XE for all X in our group. Okay, that's just the definition of the identity. Hence, the identity is in the centre. Okay, so that's good. So first off, we've shown that our set is non-empty, and we can now actually apply the subgroup test. So the point of doing that was to show that our centre is non-empty. And remember, we usually use the identity to show this because the smallest a group can be, or a subgroup can be, is just the identity by itself, so that's the one that's worth checking. Okay, so number 2, closure under the group operation. So that means we need to take two things in our centre and show that, so we'll just scribble this up here. So we want to take A and B in our centre, and show that AB is in the centre. Okay, now, so this is a set where we have to show some elements satisfy a certain property, i.e. we want to show that ABX equals XAB for all X in the group. So that's the thing we need to show. So let's just start by defining those two elements. So let A and B be members of the centre. Want to show that AB is a member of the centre. That's how we show closure, i.e. that ABX equals XAB for all X in G. Okay, so we will start that one off by saying let X be a member of G, an arbitrary one. And we're going to start with one side of this expression and try and turn it into the other. Then ABX, and I'm going to aim for X times AB. Now, I'm not going to worry about associativity. We know that just comes built in. So I'm going to freely change the order of these things as I want to, just to get the result I want. Now, A, B are in the center, so that means that AX equals XA for this particular X, and BX equals XB also. So I can take A, BX and make it into A, BX like that. And because B is in the center, that's equal to A, XB. Associativity means I got AX times B, which in turn equals XA times B, which equals X times AB, which is exactly what we want. Okay, so I'm just using the fact that because A and B are in the center, I can freely shift X to the other side of them. All right, so that's closure. The last thing we need to show using the two-step subgroup test is inverses. So we're going to say let A be a member of the center. We want to show that A inverse is a member of the center also, which means A inverse X, A inverse X equals X, A inverse for all X in G. Okay, so for this one, I'm going to start on one side and I'm going to work my way across. So A inverse X is where I'm going to start. And I want to make use of my AX equals XA. So the way I'm going to do this, I'd like to have an A beside my X so that I can use this, take advantage of this formula to flip them around. So ideally, I would have an A here beside my X. But that's not the same expression. So I'm going to use a common mathematical trick, which is basically to multiply an expression by 1, i.e. not change it, but introduce some new symbols so that we can get the manipulation we want. So A inverse X, I'm just going to multiply this on the right by the identity. And I'm going to make the identity, I'm going to express it in this way, AA inverse, because that will put an A beside the X, which is where I want it. Okay, and that equals, I'm going to stop using parentheses now because it's clear enough what's going on. That's going to be equal to A inverse AX times A inverse. So I've taken the XA and I've turned it into an AX. And now, I've now got the identity sitting here. So that equals EXA inverse, which equals XA inverse as required. Okay, so I've satisfied all the conditions that I need to for the two-step subgroup test, which means that my center is indeed a subgroup of my group. So we'll finish off this video by just doing a couple of examples of centers of a couple of different looking groups, just to get a feel for what these things actually look like in practice. So let's begin by returning to our invertible matrix group, the general linear group of 2x2 real matrices. So just quickly remember, those are the matrices that are invertible. Okay, they have non-zero determinant. So what I'm going to do is we want to find the center of GL2R. So I want to find the set of the matrices that commute with all other matrices. We know that in general matrix multiplication is not commutative, so we don't expect to get a particularly large set, but hopefully we get some. So I'm going to say let A equals A, B, C, D be a member of the center of GL2R. It's quite a complicated thing to write. And I'm going to put some constraints on A and try and figure out what the limitations on these coefficients might be. Okay, so this is one that I'll just going to do a little bit by trial and error. I'm going to define some matrices, and because A must commute with, we must have that AX equals XA for all X. I'm going to choose some arbitrary matrices X and see if I can use these to develop some constraints on my entries A, B, C, and D. So I'm going to start with this one here. I'm going to let's define the matrix B1 to be, I don't want it particularly complicated because I want things that are going to come out nice and easy for me. So if A is in the center of GL2R, then it must certainly commute with this matrix here. Okay, I've just kind of arbitrarily chosen this one to be relatively simple structure while still meaningful. So if I compute A, B1, I will get B, A, D, C. And likewise, if I compute B1A, okay, I am going to get C, D, A, B. Okay, so you can check that for yourselves, but if I multiply my general matrix A here on the left and the right by B1, then I get these two matrices here. And what this shows me is, because this must commute, corresponding entries in these matrices must be equal, and therefore, just applying this particular choice of matrix B1 here has shown me that B must equal C. Okay, we get that here and also here. And similarly, A must equal D. So A must be of the form A, B, B, A. Okay, and we know it's invertible, so we also have the determinant A squared minus B squared is not equal to 0. Okay, is that enough? Well, I don't know. Let's try another one. Let's try B2 equals 1, 1, 0, 1. Again, I know the identity is not going to help me, but maybe this matrix here will be useful. So A, B2 is equal to, again, you can check my calculation. So I'm using my updated version of A, since I've already figured out some things about it. So A times B2 is just going to be the matrix A plus B, B, A plus B, and similarly, B2A is going to be A plus B, A plus B, B, and A. Okay, and what does that tell us? Well, that gives us, well, we can see from this first one, this one here, A plus B has got to equal A, which means B equals 0. And if B equals 0, then the rest of this matrix is going to match. So that's the only piece of new information we got. So we get B equals 0. So now our matrix is turned into A, 0, 0, A. Okay, so the question is this enough? Well, we can also write this as A times I. So I can keep throwing these test matrices at it and to try and get more constraints on my entries, but at some point in time we're going to stop getting any new information here because we'll find a matrix in the center and it will keep commuting and we won't be able to make any further constraints on it. So if I take a matrix AX now, so now I'm just going to choose an arbitrary X from GL to R. Then A times X is equal to A IX, which just equals AX, which equals AXI, and I guess that scalar can move to wherever it wants in the multiplication process. So actually, AI commutes with X. So A is an element of the center. And if we just put the invertible requirement on it, that just means that A is not equal to 0. So yes, our two constraints that we came up with were enough to completely determine the structure of A because that matrix A there does commute with everything in GL2R, and so we're actually finished. The last thing we'll do is just write that down in set notation. So the center of GL2R is just equal to the set AI where A is not equal to 0. Okay, so we've done it. Right, so we'll do one more example, and that is to find the center of D4, the dihedral group of order 8. Okay, so just remember there are two types of transformations. There are reflections, which we'll call F, and there are rotations, which we'll call R. So the F was our H, V, D, and D prime, and the rotations were our R0, R90, R180, and R270. Okay, so note that for all of the reflections, the order of the reflection is 2. That's because if you reflect and then you reflect again, you get back to where you started. So we get if f equals r naught, or f is therefore equal to its own inverse for all reflections. Okay, that's the first little piece of information to note, and this formula here is probably going to come in useful. The next one, the rotation. So we're going to just go through these different types of things in turn and figure out what can and can't be in the center. So first off, we saw from the Cayley table, or the multiplication table when we first looked at D4, that rotations all commute with each other. Doesn't matter which order you do your rotations in, you'll get the same result. No matter which way around. So all commute with each other. This is not enough to put them in the center, however, because remember, to be in the center, an element has to commute with everything in the group, not just a subset of them. So rotations all commute with each other. In fact, they form a cyclic subgroup. And that can be generated, as we looked at previously, by R90 or R270. Okay, so rotations are a good candidate, so do they commute with reflections? Okay, so far we've got that our rotations commute with all the other rotations. If they also commuted with all the reflections, then we'd be all good. So I'm going to take a reflection F, and I'm going to multiply it by R, and we're going to see what happens. Okay, so note, if R, that is a reflection. If we reflect it and then rotate it, we're still on the back side of our piece of paper. So that means that we can use this formula here. So if R is equal to its own inverse. And we're just going to manipulate this and see what happens. Okay, socks and shoes property says that's equal to R inverse times F inverse. And we know that F is its own inverse, and so that's going to be equal to R inverse times F. Okay, if we assume that R commutes with F, then if R also must be, or must satisfy, if R equals RF. Okay, so if we're assuming that our rotation is in the center, i.e. that it commutes with F, then that gives us this constraint to go with this one. So if R is equal to these two different things, therefore if R is equal to RF, which is also equal to R inverse F, and thus, by cancellation, R equals R inverse. Okay, so we've pretty much got everything we need now. So what can we conclude from this? Well, no reflection commutes with all the rotations, okay? They only satisfy the R equals R inverse ones. So no reflection commutes with all rotations. Okay, because if they do, then that requires that R equals R inverse, and that is not true for all of the rotations. And the only rotations with R equals R inverse are R naught and R180. And so, but for those particular cases, they do commute with all the reflections. They also commute with all of the rotations. And so those two items are actually the center of our dihedral group. So the center of that is R0, R180. Now this is one that's a little bit tricky to get your head around, so you may want to just go back over this and follow through the argument step by step again, just to satisfy yourself that it works. But essentially the argument went, I'm going to start by considering rotations. First off, I showed they commuted with each other, all of them do. And then I said, let's assume that a particular rotation R commutes with a reflection, a general reflection F. That implied that R equals R inverse. So it meant of the rotations, only the ones that satisfy R equals R inverse were allowed in. And as for the reflections, well, this thing we just did over here also said that only the reflections do not commute with R90 and R270. Okay, so my arbitrarily chosen reflection here does not commute with R90 and R270 because this comes from the reflection commuting, and therefore I can exclude all of those just out of hand. So the center of D4 is just R0 and R180. So I think that's about enough for this video. So we've studied the center of a group, and we've shown that it's a subgroup, and we've looked at a couple of nice examples of this. So we'll pick this up next time. Until then, ka kite anō.